Section 4.5 gives us properties of logarithms. First, let's review the definition of a logarithm, which just gives us a way of going back and forth between logarithmic form and exponential form. For all real numbers y and all positive numbers a and x, where a is not equal to 1, y equals log base a of x if and only if x equals a to the y. In other words, our exponent y can be anything, positive, negative, fraction, whole number, doesn't matter. Our restrictions are on the base, which in both of these forms is a, log base a and a to the y. So our restrictions are that the base has to be positive and not equal to 1, and x in logarithmic form is the argument. It has to be positive as well because there's no exponent of a positive base that can give you 0 or a negative argument. Um, just to review real quickly, if I give you 10 equals log base 7 of q and ask you to change that to exponential form, you would say the base is 7, the exponent is 10, and 7 to the 10 would have to give you 2. So logarithms and exponential form are just two different ways of writing the same thing. Because of that, the properties of logs are all based on the properties of exponents. If x and y are any positive real numbers, and r is any real number, and a is any positive real number not equal to 1, the same restrictions we had here, the following properties are true. If you have the log of a product, that can be separated into the sum of two logs. The log of x times y can be separated into log base a of x plus log base a of y. Reading that backwards, if you have the sum of two logs with the same base, those two logs can be put together as a single log of a product. That's based on the product rule for exponents, which says if you multiply two expressions with the same base, you add their exponents. And that's what logarithms are, exponents. So if you're multiplying, if you're taking the log of a product, you can use the product rule to separate that into the sum of two logs. The log of a quotient can be separated into the difference of two logs. Or, in reverse, if you have the difference of two logs, you can put it back together as the log of a quotient. That's based on the quotient rule for exponents, which says when you divide two expressions with the same base, you subtract their exponents. Subtract the bottom exponent from the top exponent. So the difference of two logarithms can be put back together as a log of a quotient based on the quotient rule for exponents. Property C says log base a of x to a power can be written as the power times log base a of x. What we usually say is if you have log of something to a power, you can bring the exponent out front, but you're bringing it out front to multiply it by the log, and that's based on the product rule for exponents. If you have log of something to a power, you multiply the exponents. Log base a of x is an exponent and r is an exponent, so you multiply them. These last three properties we talked about yesterday. Log base anything of itself is 1 because anything to the first still gives you itself. Log base anything of 1 is 0 because anything to the 0 gives you 1. And then finally, this was our theorem on logarithms. Logarithms are 1 to 1. If you have two logs that equal each other, then their arguments have to equal each other as well. All right, before we do some problems, let me caution you of two other things, mistakes that are commonly made. Occasionally, I'll have someone try to distribute the log through a sum, log base A of the quantity x plus y. You can't just distribute that log as if it were a constant. If this were just a number like 5, then you could multiply the 5 times the x and the 5 times the y. But log's not a number, log's an exponent, and you know that you can't distribute exponents through a sum. For example, if you have x plus y squared, you cannot just square the x and square the y. Distributing a logarithm would be just about that same thing. So that's not true. And also, if you have the log of a fraction, you can't just take the log of the numerator and the log of the denominator. We already have a quotient rule for logarithms that tells us how to separate the log of a fraction. You separate it into the difference of two logs. So make sure you don't make that common mistake. All right. In tonight's homework, you basically have three kinds of problems, and most of them involve this property A, B, and C. Your first set of directions say take this logarithm and separate it into logs of just x or just y or just z. Instead of log of a product or log of a quotient, take the logarithms apart. The second kinds of problems say, I'm going to give you a sum or difference of logarithms, and you go backwards, put it back together as a single logarithm. And then our third kind of problem today is just going to be some practice, some more practice solving equations. So let's look at some problems from the book. This is page 336 in the 11th edition. And the first problem that I want to work is number 6. Log of square root of y divided by x to the 4th times the cube root of z. The directions say express in terms of logarithms of just plain old x or plain old y or plain old z. The first thing that I'm going to have to do is rewrite these radical expressions with exponents so that I can use property C later. What exponent means the same as square root of y? That's y to the 1/2. And in the denominator, cube root of z is z to the 1/3. Now I just want to use my properties of logarithms to separate that into a sum or difference of logs. The first thing I know is that I have a log of a quotient. That quotient can be taken apart. The log of a quotient can be separated into the difference of two logs. So I'm going to separate that quotient into log of the numerator minus log of the denominator. And that's using my property B of logarithms. But the directions say that I just want logarithms of plain old x, plain old y, or plain old z. I don't want these exponents here, and I don't want log of a product left in that second term. I'm going to use the property A of logarithms, which says I can rewrite the log of a product as the sum of two logs. So I will take apart this term as the sum of two logs. I'll deal with those exponents in a minute. Now, I've made a very deliberate mistake because it's a common one. I wanted you to see it. I did say that a log of a product is the sum of two logs, but can you see why this line is not equivalent to the line above it? If I was subtracting this log of a product, then I have to subtract this whole sum of two logs. Without those parentheses, that expression's not equivalent to the line above it. So you need to either be careful to use those parentheses or go ahead and distribute the negative completely. There's one other thing that I need to do before I will have done exactly what the directions ask, and that is I want log of y, not log of y to the 1/2. So what can I do with that 1/2? Property C tells me if I have log of something to a power, I can bring the exponent out front and multiply it by the log. In other words, on number 6, I can bring the 1/2 out front and make it the coefficient of the log of y. And similarly, I can do the same thing with the 4 and the 1/3 that are exponents of the x and the z. I'm going to go ahead and distribute that negative and bring those other exponents out front in the same step. And now I've done what the directions ask. I have log of plain old y, log of plain old x, log of plain old z. We'll do another problem separating logarithms like this, and then we'll turn around and practice if you give me this sum or difference of logarithms, can I put it back together as a single logarithm? Both of those skills have their place going forward in math. You very often have to put logarithms together to solve a logarithmic equation, and you'll see that today. What you won't see today, maybe not until you get to calculus if you're going there, is the purpose of taking logs apart. You put logs together to solve an equation, but in calculus, taking an expression like this and dividing it or separating it into these three terms makes it easier to find the derivative, which is one of the big goals in calculus. So both of those skills have their place. All right, let's do one more taking logarithms apart. Number 8, natural log of x times the cube root of y to the 4th divided by z to the 5th. Like number 6, the first thing I need to do is rewrite that expression without the radical. Cube root of y to the 4th over y to the 5th can be written as y to the 4th. I didn't mean y to the 5th, I meant z to the 5th. That whole thing to the 1/3. And then perhaps I'd like to clean that up a little bit before I actually use my properties of logarithms. I would remove these parentheses by saying when you raise a power to a power, you multiply those exponents. I may also put that x over 1 and write that as natural log of a single fraction. My single fraction would be an x in the numerator, a y to the 4/3 in the numerator because I've multiplied those exponents, over a z to the 5/3 in the denominator because I've multiplied those exponents. I haven't used my properties of logs yet. I just simplified that argument before I started using the properties of logs. Like number 6, first thing I notice is I have log of a quotient. Now, actually, I'm going to tell you something, and you may have already noticed this, but it'll save you a couple steps. Think back to when we first talked about negative exponents. If I gave you an expression like a to the negative 2b cubed c to the negative 4, when you were first learning negative exponents, you may have written the middle step of writing this as 1 over a squared times b cubed times 1 over c to the fourth. And then you got to the point where you just said those factors with negative exponents go in the denominator, and the factors with a positive exponent go in the numerator. I don't really have to write this step anymore. Well, because logarithms are exponents, we should be able to find a parallel that allows us to skip a step in number 6. Notice that the x and the z that originally were in the denominator, they both had negative coefficients. It's just like this a and the c, which are both in the denominator, both had negative exponents. So I could have skipped this step if I had just known anything with a positive coefficient came from the numerator. This y, I can tell it came from the numerator. Anything with a negative coefficient came from the denominator. Or any factor from the denominator, when I take this logarithm apart, that factor is going to have a negative coefficient. Let's use that in example 8 to save ourselves one step. I'd write that as the log of a product can be taken apart into the sum of two logs, and then the log of a quotient, or that z, because it's from the denominator, should be subtracted. And then finally, I can use property C, which says log of something to a power. I can bring that exponent out front. So I've done all that the directions ask me to do. I have a log of plane X, a log of plane Y, log of plane Z. All right, let's practice putting logarithms back together. Number 12. I'll give you just a second to copy that down in your notes. And the directions say write each expression as a single logarithm. So we're practicing putting those three logs back together as a single log. And I'm going to see if we can do this in just one step. I know that because the log of x has a positive coefficient, that x came from the numerator. And I know that because the log base a of 3x minus 4 has a negative exponent, that expression came from the denominator. And similarly, this 5x plus 1 came from the denominator. If I go ahead and put the 5 back as the exponent of the x, I can put it in the numerator. Put the 1/2 back as the exponent of 3x minus 4, and put it in the denominator. Put the 3 back as the exponent of 5x plus 1 and put it in the denominator. I've done that problem in one step. Nothing about this argument can be simplified. I have a single log of a single fraction, and that's all the directions ask me to do. Sometimes I have to clean up this argument, but there's nothing to clean up in number 12. Let's look at number 16. I can put that together as a single log in just one step. If I put the 2 back as the exponent of the x and put that factor in the numerator because it had a positive coefficient, I could put the 4 back as the exponent of the 1 minus y, but it goes in the denominator because the coefficient of that term was negative. And I can put the 3 back as the exponent of xy, and it goes in the denominator because that coefficient was negative. Notice at this point, I still have those parentheses, and that is not in simplest form. That's going to require a little bit of cleaning up after I've put the expression back together as a single logarithm. So let's see how I can clean that up. Removing parentheses, I can say 1 to the 4th is still 1, and then y to the 4th is y to the 4th. And the second factor, when I remove the parentheses, will become x cubed y cubed. I can put that over 1 if it helps me see better what will cancel. In the denominator, I can say this y cubed divides in that y to the 4th and just leaves y to the 1st here. I think I'm going to take 2 more steps to finish this. I have x squared, natural log of x squared over this denominator becomes x cubed over y. And how do you divide a whole number by a fraction? You divide a whole number by a fraction by multiplying by the reciprocal of the fraction. Multiply the x squared by y over x cubed. Some brackets there would help me see that natural log is of that whole expression. I can put the x squared over 1, divide the x squared into the x cubed, and that simplifies to natural log of y over x. Remember the directions here said write as a single logarithm. I could separate that into log of y, natural log of y minus natural log of x, but that would be 2 logarithms, and the directions said write with only 1 logarithm. So there it is. All right, the last thing you have to practice in this section is solving equations. And we're going to have some notes in 4.6 summing up kind of everything I'm about to say. solving logarithmic equations. Logarithmic equations are usually in one of two forms. Either you have logs on both sides of the equation. I can show you one from the book. For example, number 19, if you have logs on both sides of the equation, single logs with the same base, then you just take the logs off and set the arguments equal to each other. Now, before I would do that on number 19, I would need to put the 2 back as the exponent of the x and the 3 back as the exponent of the 5. But once I had a single logarithm with the same base on both sides of the equation, I could just take the logs off. The other scenario we'll run into is when we have logs on one side of the equation and a constant on the other. We'll figure out how to solve that in just a minute, but first let's do a problem with logs on both sides of the equation. And I've chosen number 18. I mentioned a minute ago that one reason we need to know how to put logarithms back together is to solve logarithmic equations. On this right-hand side, we have the sum of two logs, and we can't use our theorem that says if you have two logs that equal each other and have the same base, then their arguments almost must also be equivalent. We can't use that unless we have single logarithms on each side of the equation. So I need to write that right-hand side as a single logarithm. And my property A tells me that the sum of two logs can be put back together as the log of a product. In other words, I can multiply that 5 times 3. And that right-hand side is equivalent to log base 4 of 15. After I have both sides being single logarithms with the same base, then I can say, therefore, the arguments must be as equivalent as well. Then I'm just solving a linear equation. Subtract 2 from both sides and divide by 3. You get the possible solution, 13 over 3. Remember, the thing you're watching out for when solving logarithmic equations is your proposed solutions can't make any of the arguments negative. Well, 13 thirds is not going to make that negative, so 13 thirds is the solution to that equation. All right. Number 24. This one's very similar to 18. I just need both sides of the equation to be a single logarithm before I can take the logs off and set the arguments equal to each other. So on the left-hand side, I can say the sum of two logs can be written as the log of a product and on the right-hand side, I need that to be a single log with a coefficient of 1. So what can I do with the 1/2? I can put it back as the exponent of the 9. And now that I have single logarithms with the same base, these are both base e, I can say the arguments must be equivalent. And I'm going to go ahead and say 9 to the 1/2 means the square root of 9. Square root of 9 is just 3. The most illegal thing you could do now is say x equals 3 or x plus 6 equals 3. It's not true if you multiply two numbers together to get 3, one of them has to be 3. This is a quadratic equation. If you multiply, you get an x squared here. And to solve a quadratic equation, you need to get it set equal to 0. And this one, subtract 3 from both sides. And then see if you can factor. If you can't factor, you can always use the quadratic formula. Just because I know that you're comfortable using the quadratic formula, I'm going to put QF ... on this one and let you finish it on your own. I'll tell you what I got for an answer if you want to pause the video and finish working that one. You can check and make sure that you get x equals -3 plus, actually you would come up with plus or minus 2 square root of 3. But if you use the negative, -3 minus 2 square root of 3 is going to give you a negative number, and you can't take the log of a negative number. That's why I don't have -3 plus or minus 2 square root of 3 there. You just can't use the negative as part of this solution. All right, I have two more problems. Number 28 is not an equation where you have logs on both sides of the equation. So we may have to use a different technique to solve it. I have 2 logs on the left-hand side, and I can put those back together as a single log, but then I just have a constant on the right-hand side. Let's go ahead and put this left-hand side back together as a single log, and then we'll figure out what to do next. The sum of 2 logs can be put back together as the log of a product. And if this right-hand side were log base 3 of 2, then I could just take the log base 3's off and set the arguments equal to each other. But it's not, it's just 2. Do you remember how to solve an equation, a logarithmic equation, if you have log equals a constant? You can just change it to exponential form. The base is 3, the exponent is 2, and 3 squared equals x minus 2 times x minus 4. Because I know I'm going to have to anyway, I'm going to go ahead and multiply those two factors. Get x squared minus 6x plus 8. And then I'm going to have to subtract 9 from both sides to get that quadratic equation in standard form. Once again, I just happen to have a quadratic equation where I can't factor the quadratic expression. So I would have to use the quadratic formula to solve that equation. When I do use the quadratic formula, I get 3 plus or minus the square root of 10. But 3 minus square root of 10 is a negative number, and that would make both of these expressions undefined. A negative minus 2 would be a negative minus 4 would be a negative, so I could not let x be a negative number in the original equation. That's why the solution is only 3 plus square root of 10. All right, last one, number 34. I chose to do a problem like the ugliest one in the homework. Make sure that as you copy that down, you notice this is 4 to the log base 4 of 3. And I do have logs on both sides of the equation, but I also have strange stuff over here. This is a logarithm, but think about it. Log base 3 of 9. Is there something simpler than I could put in the place of log base 3 of 9? Can you evaluate log base 3 of 9? The exponent of 3, which gives you 9, that's just 2. And what about this? 4 to the log base 4 of 3. 4 to the log base 4, just undo each other and leave me a 3. So if I got these two logs on the left-hand side of my equation, and I just wrote those as constants, it would be a problem very similar to number 28. I'm going to subtract the log base 2 of x minus 3 from both sides. And on the right-hand side, I'm going to say log base 3 of 9 is 2. And 4 to the log base 4 of 3 is just 3. And just like I can put this 2 and 3 together, I can put these two logs together. The difference of two logs can be written as the log of a quotient. And that right-hand side is just 5. Now this problem's very similar to where I was here in number 28. I have logs on one side, a constant on the other. I just changed this to exponential form. The same way on number 34, if I change this to exponential form, the base is 2, the exponent's 5, 2 to the 5th equals x plus 3 over x minus 3. And then I can just say 2 to the 5th is 32. And then what? I need to multiply both sides by x minus 3 to clear out the fractions. Distribute the 32. And solve that linear equation. Just subtract x from both sides, add 96 to both sides, and divide both sides by 31. Kind of seems like that ought to reduce, but I don't believe it will. 31 is a prime number. So here we have a number that's a little bit over 3 point something, and anything bigger than 3 would be fine in both of those logarithmic expressions. 3 point something plus 3 is positive. 3 point something minus 3 is positive. So 99 over 31 is the solution to that equation. All right, I think that's enough examples. You can practice taking logarithms apart, putting them back together, and then solve a few logarithmic equations. I have one bonus news for those of you who watch the video. I'm going to tell you that you can actually stop that homework at number 33. There are some graphing problems after that on page 336, but I don't really care if you do those or not. So the homework for 4.5 is just 1 through 33 odd instead of 1 through 45 odd. Have a great day.